Okay, so in this video we will try to see how we can obtain the far field distribution or far field pattern of an illumination device. In this case, I have chosen a work of mine where I have tried to extract the far field profile of a laser. So in the left figure, we can see the far field distribution actually of a laser, and along the x-axis there lies the theta x, and along y-axis the theta y exists in degrees. And in the right figure, we can see that the far field intensity distribution, where along x only the theta x exists, and along y we try to plot the intensity profile only along x-axis while keeping the theta y equals 0 degree. So now I will show you how you can extract these curves or these results. So let me go back to my simulation file. Okay, not this one, sorry, this one. So after running your Lumerical file, you have to for seeing or for viewing the far field, I have taken a very simple DFT monitor in the transmission side. So this is the transmission side of my device, and this is a very normal the DFT monitor. So after running the file, then right click on this DFT monitor, from the visualize go to the far field, and now actually my laser is designed to laser at around 870.055 nanometer. So I just have to type that value. Okay, so I want to see the far field intensity profile at this wavelength. It's around 870 nanometer. So after you put your desired wavelength value here, go to the far field settings. So I have used the top hat illumination option for uniform illumination across the whole device, and I have assumed 200 periods along both x and y axis, and only one period along z. And for better resolution, I have taken 2001 points. So after giving these values and after selecting this particular wavelength, hit OK and wait for a while. So this new window has popped up. Okay. So basically you need to take ux along this and uy along this, the wave vectors actually, the wave vectors components ux and uy. So first fix this ux along x and uy along y axis. It will get updated a little while later. Okay, so ux along this, uy along. So if you zoom now, so yeah, this is the same profile that we saw earlier, this one. So here you can see that it's actually theta x and theta y, but what we are seeing here, ux and uy in terms of wave vector components. So what we need to do, well, first of all, we just need to keep the real part of E square, that means the intensity. We know that absolute value of E square is proportional to intensity of light. So let us delete the other two parameters. This one remove, and take some time because this is a very large file. And also remove this. So basically we are left with real part of e square only. Okay, so do not do anything else, because we are already getting the e square curve here, that is the intensity curve. So what we will do now, we will first have to export it to MATLAB script. So hit this button, MATLAB export script, and give any name, far field, save it. So also you first need to turn on the MATLAB integration setting in your PC first, in order to uh, get this, what should I say, it is this kind of scope, or well, let this open first. Well, so here we can see the profile along UX and UI. So basically we now have to do some post processing. So let me open the code first. So yeah, you need to install MATLAB first and do some necessary steps to set up your MATLAB and to integrate MATLAB with your Lumerical. So this is the code actually. Uh, we run, okay. To brackets. Okay, you have to put brackets manually in order to see the profile. So now what we will do, we have to modify this code. Let me show you what I did. Okay, so I have modified the exported code a bit. So let us see step by step. So after loading the data, we have to apply some formula in order to convert this UX and UI, that is the direction cosine UX and UI, to theta x and theta y. So these are the formulas. These formulas are applicable uh, for small angles, small diffraction angles. So if we go down, as I showed you earlier, well, I tried to normalize this profile, in this case from 0 to 1. So what I basically tried to do, this code, I first tried to find the max value of this whole profile, the intensity profile, and afterwards I try to normalize all the values with respect to this max value. And yeah, in the using the rest of the code, I tried to plot it, and let me run it now. So here we can see the actual picture that we wanted. So this is the far field pattern along x and y axis both, and U square means the intensity, the light, at 870 nanometer. And see the scale, it's normalized from 0 to 1, and we can see that the light is centered at 0 degree, and the light intensity drops off sharply as we move from the center or 0 degree along x and y axis. So Afterwards, if you want to use this in your paper or anywhere else, you can simply go to File and Save. Okay, just hit Save, and you can export it to any any format like .pdf or .png or .jpg, in any kind of format. Okay, so this was our first part, and now if we want to view or visualize this second graph, which is e square versus theta x. So yeah, for this we have to plot a different kind of graph here. So let us go back here in this the same far field pattern. Now you have to go to the line setting. So in the line setting, you can see this kind of curve. So basically, this from this curve you basically cannot get any kind of idea, and we plotted this for theta y equals 0. So to set up this plot, you first need to select uy equals 0 first. So from this here you can see uy, you can change the slider, and basically by changing the slider, stop where you get the 0 value for uy. Okay, for this index we are getting uy equals 0, and now we are getting some kind of meaningful result, but still we need to convert this ux to theta x, and along this the e square exists. So we have to like follow the same step, like export MATLAB script. Let me name it theta x. It will open a window, this window. And okay, let us open the code now. This is the code, the generated code. So let us first run, and then we will do the other necessary modifications like we did earlier. It's not actually plotting the results. We did it right though. Well, let me modify the code. Just give me a minute. Well, I think there was some kind of problem regarding naming, so I just okay, I just exported it and just renamed it to theta x1. And after exporting this, the code that I obtained, I just did some modifications to it in order to convert this ux to theta x using this sine dux formula, that is sine inverse ux. And here also I tried to normalize the curve from 0 to 1. Basically I first found out the maximum electric field intensity value, and then divided all the values by this max value. So yeah, after following this code, and make sure that you put these brackets, okay, and these commas. So after preparing this code, you just hit the run button. You can get this exact far field profile that we tried to simulate right from the beginning of this video. So yeah, along the x-axis only the theta x exists, and along y-axis the intensity is shown here. And yeah, this curve is for theta y equals 0, and in order to set theta y equals 0, that means we are only varying the theta x, or the angle along the x-axis. In order to set theta y equals 0, the condition was to first use this slider and make uy equals 0 from this option and then export it. So this concludes this video on far field. I guess I have tried to show everything that you needed to know, and make sure that you take the help of internet to modify this code. Okay, so yeah, thank you.